At long last we come to center of mass. Center of mass is increasingly important as the complexity of the physics problems that we solve likewise becomes increasingly important. When we're doing momentum problems, and when we're doing energy problems, and when we're doing force problems, everything that we've done up to this point in time has been a study of translational motion. We've been treating every single object that we've analyzed as if it were a spherical cow, a perfectly round, perfectly small, tiny little particle that behaves with all of its motion all together in just one or two directions. Real objects aren't like that. Real cows aren't spherical. They can roll around like a ball. They can flail about like a person, like a toddler running from somebody that's trying to tickle them. They can flip and move and bend. One part of their body can go in one direction, the other part can go in the other. Think about how you walk. Your overall net translational motion is forward. However, your legs lift up and down. Your hips swing at the joint to allow you horizontal motion. Your arms and your legs move in opposite directions as you travel. So that means that real objects have all sorts of motion, right? Take a look at this diver here. This would be the perfect, more similar to the spherical cow model of a diver, in that their body stays perfectly rigid and then their body travels this net pathway of projectile motion. You know the truth is that that's not what happens. This body changes and does all sorts of funky motion. We call general motion the rotational and translational motion together. So all of that flailing and rolling is just the general motion that you experience or see on a day-to-day basis. There is one point, and that one point moves the exact same way the whole time. And that one point is the center of mass. So we give the definition center of mass, which is the sum of the translational motion of the center of mass plus the rotational mass around the center of mass, and all of the vibrational and all of their types of motion. So the center of mass gives us the sum of all motions. The center of mass gives us this net pathway to travel regardless of how the rest of the object travels. So it's really convenient to know how to find the center of mass. So, even if an object rotates, or several parts of a system of object move relative to one another, right? This diver, she rotated. Her head started up here, then it went here, then it went down, and then she came back up, and then her head went down. So she rotated around as she flipped. Or if several parts of a system move relative to one another, her hands go up, her legs go down here. Here, her legs, they went from down, they swung back, and her hands went from up, they swung forward, so they moved relative to one another. One point, her center of mass, just like a sphere, would move just like a spherical cow. If we pretended that she was a spherical cow, she would follow this one point pathway. And you can see that all motion that occurs relative to a center of mass. Take a look at the video of the screwdriver getting thrown through the air. So we can find the center of mass for any system that's made out of matter, any system that's made out of particles, no matter how many particles they're made out of. Let's first consider a super simple system that's made out of two particles, one particle with mass A and one particle with mass B. If there's two particles, those two particles could be connected along a line, and we can call that line our x-axis. We can find the center of mass between those 2 points by using a simple calculation. So we're going to set the axis between the 2 points, and we'll use this equation which says that the center of mass lies somewhere along the x-axis, right? It's somewhere in there. And where it lies is going to be given by the mass of object A times the displacement of object A compared to the mass of object B compared to the displacement of object B. So that means we're going to have to set some sort of a reference point, and then it's going to be a ratio of the mass and displacement for object A and B divided by the sum of the masses. And when we say the sum of the masses, we just call that a big capital M. So M is equal to the mass of object A plus the mass of object B. Here's a neat thing. If the mass of object A and B are equal, then we would set the center of mass equal to M time distributed to the displacement of A and B divided by 2M. In other words, for a system where the 2 objects have the exact same mass, the center of mass between them is going to be given exactly halfway between the 2 objects. If one mass is greater than the other, the center of the mass is always going to be closer to the more massive object. So here's an example looking at center of mass. All right, if we set our axis, here's our y-axis, here's our x-axis. You only have 2 objects here, and so we can set them on an axis. Here's object mass A and object mass B. Here we have a reference point, and that's exactly what this is here. It's our reference. And you need that reference because you need to figure out where the center of mass is going to be, and that number is going to be away from the reference point. So here we can take a measurement where this is the position of object A compared to that reference point right there. This is the position of object B compared to that reference point right there. Here's MA and MB. And if we plug that into the equation, XCM equals MAXA plus MBXB divided by M, you get the XCM is right there compared to this reference point. So that's how those values are going to be determined, and that's how those values are going to be calculated. Let's go ahead and take a look at an example. We're going to find the center of mass of 3 guys on a raft. I don't know what they're doing on the raft. I don't know why the raft is so big, but we're going to figure out where the center of mass is. There are 3 people who roughly have the same mass. So we're going to say that bro guy 1, bro guy 2, and bro guy 3 all have the same mass. And they are on a lightweight air-filled banana boat, which we can neglect the mass of. And we're going to say that all of them are perfectly along an x-axis, so that if this is our reference point, dude A, bro guy A, is 1 meter away, bro guy B is 5 meters away, and bro guy C is 6 meters away. We're going to use this information to determine the center of mass of the boat. And we get to ignore the mass of the boat to do this, so we're just going to find the center of mass. There's 3 objects here, so we're going to set all 3 of them. This is guy A, this is guy B, this is guy C. They all have the same mass, M. So it's going to be M XA plus M XB plus M XC divided by capital M, which is XA M. So here M equals M plus M plus M. So that's going to be equal to 3 little m. So that means that M XA plus M XB plus M XC divided by 3m. There's some factoring that we can do here, so we're definitely going to do that factoring. We're going to pull out that m XA plus XB plus XC all over 3m there. and I can get rid of that m. So since they were all roughly the same mass, that's pretty convenient. And now I'm going to plug in my actual values. And here my actual values are 1 meter plus 5 meters plus 6 meters divided by 3. So 1 plus 5 plus 6 is 12 meters divided by 3. So that means that the center of mass is at 4 meters. So the center of mass is right there at 4 meters from the reference point. And remember to always establish what it is from your reference point. Here we decided that our x-axis was along the water and the y-axis was up. If these objects didn't fall along one axis, we would have had to have broken it down into multiple axes. You can do this for objects in both the x and the y direction, and you just have to add center of gravity in multiple directions to do it. So here's what that would look like. If the particles are spread out in 2 or 3 dimensions, then you're just going to figure out the mass stays the mass the whole time. You'll have to figure out a reference point in the x direction, a reference point in the y direction, and if you have it, a reference point in the z direction, and all of your measurements should be taken from that reference point, and you would be able to determine xcm, ycm, and zcm, and you should be able to plot it, and then you would know the center of reference. Now, we're going to talk about a value that's similar to the center of mass, but a little bit different. It's the center of gravity. Center of gravity is given as the point which gravity acts on an object. And for most relative purposes, the center of gravity and the center of mass are the same thing. The center of gravity is what we consider the point where all of the force of gravity is acting on the object. So it's the sum of how gravity is pulling on every single one of those particles, and that sum can be found right at that point. The real difference between center of gravity and center of mass exists, but for all practical purposes, the center of gravity and the center of mass can be considered to be the same point. A lot of the times it's easier for us to figure out the center of mass or the center of gravity experimentally instead of just actually calculating it. And you can do that by using a pivot point or figuring out what the pivot point is on an object. So if you have an object and you set it up on a pivot point, right, on a y-axis, that object is going to swing back and forth unless the center of gravity is located directly on that line below the pivot point. All right, if that happens, then you know exactly where that center of mass is. If you've got a nice symmetrical object like this, you only need one pivot point. If, however, your object is asymmetric, you're going to need 2 pivot points, and the 2 pivot points, once it stops swinging, will give you a center of mass. So this is an asymmetrical object, so this object is going to swing back and forth on its axis until its center of gravity is located directly below it. Since it's not the same on all sides, you're going to need a second pivot point to suspend it from, and that center of gravity is going to be located at the connecting point between the 2 axes of where that pivot point has been hung. And as the object gets more asymmetrical in another dimension, you're going to need a 3rd pivot point to find it. But for all calculating purposes, you can calculate the center of gravity and assume that it's going to be the same as the center of mass.